Hello everyone. In this video, I would like to talk about the first derivative test. Now this test, it takes some of the ideas that we've already discovered about derivatives and it combines them together and it gives us a way to find the local maximum values or the local minimum values. So a couple of the ideas that we're going to use here, the first one is a critical number. Now remember, a critical number occurs when the derivative is either equal to 0 or it's undefined. Also, we know that when the derivative is positive, we know that means that the slope of the tangent line is positive, which means that our function is increasing at that point. And if our derivative is negative, it's just the opposite. The slope of the tangent line is negative, which means that the function is decreasing at that point. So we're going to combine those together, and it's going to give us a way where we can take a function and we can find our local maximums or our local minimums. So to start off with, let's just read through what the derivative test says. It says, let f be a function that is continuous on an interval I. Suppose that c is a critical number of f, and ab is an open interval in I that contains the point c. And we have a couple different options here. So the first one, if f prime of x is greater than 0 for a is less than x, which is less than c, and f prime of x is less than 0 for c is less than x, which is less than b, then f of c is a local maximum value. There's a lot going on here, a lot of inequalities, so let's just break this down and see what this is saying. So back in the beginning of this bullet point, if f prime of x is greater than 0, so if the derivative of our function is greater than 0, so if it's positive, for this range of values in between a and c, and then if on the other side of c, so now it's the second half of our interval from c to b, now the derivative is less than 0, so the derivative is negative, then it's a local maximum. So in other words, what we have is on the left-hand side of our little interval, the derivative is positive, meaning it's increasing. And then on the other side of c, our derivative is negative, meaning it's decreasing. So we're going from increasing to decreasing, which creates a maximum. The second bullet point says the exact same thing, but it's just reversed. So now our derivative starts negative, so now our function is decreasing. And then on the other side of c, our function is increasing because the derivative is positive, and that's going to create a local minimum value. And then the last bullet point here says that if the signs are the same on both sides of our value c, then it's neither a local minimum or local maximum. So basically, if I go from increasing and it stays increasing, I don't have a local minimum or local maximum. Now let's also put a picture with this, just so we can make sense of what the first derivative test is saying even more. So I'm just going to draw a random function. It's going to go up a little bit, it'll come down, and I'll just continue on like this. And now let's take a look at our local maximums and minimums. So it looks like about right here, we're going to have a local max, and I'm going to just call this x1. So this is going to be our value of c. So c is a critical number, so x1 is going to be our critical number. And as you can see, on the left of our critical number, our function is increasing. It's going up. That means that the derivative is positive because the slopes of all of these tangent lines are positive. And then once we get here, we are going to have a horizontal tangent line, meaning the derivative is equal to 0. And as soon as we get onto the other side of x1, then we start going down, which means my derivative is negative. All the slopes of the tangent lines here are negative. So that creates a local maximum. So we go from increasing, it switches to decreasing, we have a max. And then over here, this is just the opposite. So it looks like we have a local minimum here, and let's just say that this is x2, and now we're going from decreasing, so we're going from negative slopes of tangent lines, and that's switching to now we have positive slopes, so now my function is increasing, so that's going to create a local minimum. So this lays out the requirements for a local max or a local min, but it also more or less details a process we can use to find our local extrema. So I want to talk about that process next. I have a function f of x is equal to x cubed minus 3x squared plus 5. So what this process involves, we're going to find the critical numbers. The critical numbers are going to give us possibilities for a local maximum or a local minimum. And then we're going to test the intervals around our critical numbers to see whether they're increasing or decreasing. Whenever we have a switch from increasing to decreasing or vice versa, we know that we have a local extrema. So to start off with, let's find our critical numbers. So we're going to need the derivative. So f prime of x, I can just use my power rule for each of these terms. We'll get 3x squared. And then my second term, bringing that 2 down, 3 times 2, we have minus 6x. And the derivative of 5 is just 0. Now to find the critical numbers, we're going to set this equal to 0. So we have 0 is equal to 3x squared minus 6x. And what I'm going to do here is I'm actually just going to fully factor this because I want to take a look at the factored form a little bit later on. So if we factor, looks like we can take out a 3 and an x from both terms. So we have 3x times x minus 2. And here I can see that my two critical numbers are going to be x is equal to 0 or when x is equal to 2. So at 0, at 2, we have the possibility of having a local minimum or a local maximum. Now to make sure, we're going to test the intervals around these two critical numbers. And the way that I like to do that is by using a sign chart. So I'm going to think about my number line, and my two critical numbers are going to split my number line up into 3 different intervals. So it's going to split it at 0, and it's going to split it at 2. So the intervals I have here, I have all the numbers from negative infinity to 0. I have the numbers in between 0 and 2, and then we have the remaining numbers from 2 to infinity. I just want to find whether these intervals for the derivative, I want to know if they are positive, meaning my function is increasing, or if they're going to be negative, meaning my function is decreasing. So I could pick out a specific number and test it, but I am just concerned with the sign. Is it going to be positive or negative? So that's why I like to take a look at the factored form. So for the first interval, something that's less than 0, so it's a negative number, so 3 times a negative, so this first part will be negative. A negative minus 2, that's going to stay as negative. So I'll have a negative number times another negative, which means I'm going to end up with a positive. So that means that my function is increasing on this interval. In the middle, so in between 0 and 2, again, maybe I'd want to pick out a specific number like 1, that would be easy enough. But it's something bigger than 0 and less than 2. So it's positive, so 3 times a positive number, this will be positive. And then something smaller than 2, if I subtract 2, that will give me a negative number. So I have a positive times a negative. So all the slopes of the tangent lines in this interval have a negative slope. So that means my function is decreasing. And then our last interval here, something bigger than 2, it's still positive. So 3 times a positive is positive. Something bigger than 2, if I subtract 2, this will end up being positive. So a positive number times another positive number, we end up with positive. So this interval is also increasing. So wherever we switch from increasing to decreasing, this is going to give us a local maximum. I know this is a max because my function is going up. And then I have a horizontal tangent line at 0, and then it's going back down, so it's a maximum. And then wherever my function goes from decreasing to increasing, this is going to be a local minimum. So my function is going down. At 2, I have another horizontal tangent line, and then it's increasing again, creating that minimum. And let's just evaluate our function at these 2 points so we can clearly state where our maximum and our minimum is. So f of 0, this one's easy enough. This would be 0 minus 0 plus 5, so f of 0 is equal to 5. And then let's find f of 2. We'll have 2 cubed minus 3 times 2 squared plus 5. So this is going to be 8. 2 squared is 4, so 3 times 4 I get 8 minus 12 plus 5. So that's going to be positive 1. So we have a local maximum at the point 0, 5, and we have a local minimum at the point 2, 1. So here we go. So that's the general idea of the first derivative test. Find the critical numbers, take a look at your intervals, test the intervals to see where they're increasing and where they're decreasing, and that will indicate your maximums and your minimums. Now let's just take a look at the graph of this function just to verify. So we'll use the calculator here to help us out. So if I go in here and plug this in, we have x cubed, and then minus 3x squared, and then we're going to add on 5. Now if I graph this, we might have to adjust our window. Looks like I'm zoomed in too much. So if I go to my window here, we can use some of the information we found to help us decide what sort of window we want. So our two critical numbers are at 0 and 2, so I need to make sure to include those. So I'm going to just go a little bit to the left of 0 and a little bit to the right of 2, just giving myself enough room on either side. And then we did also find our maximum and our minimum. So my minimum was at 2, 1, and the max was at 0, 5. So looking at those y values of 1 and 5, just want to make sure I include those. So in this case, I'm going to go from -2, and I need to go up to 5 at least. So I'm going to go a little bit further than that. So I'll go to 6. And now if we graph, we should be able to see most of our function. And taking a look, so from -infinity until we get to 0, our function is increasing, which we saw with our sine chart. At 0, we have a local maximum. We have that horizontal tangent line. And now it switches, and our function is decreasing until we get to +2, where we have another horizontal tangent line and a local minimum, and then our function goes back to increasing. So there you have it. So using the first derivative test to find local maximums and local minimums.